And welcome Calculus 3 students. We are looking at change of variables with our multiple integral problems. This means we are looking at doing a UDU kind of situation and extending this UDU change of variables to two dimensions or multiple integrals. Here we have one where we've changed it to double integral. And you'll note we've got this double integral. I can see that this is going to be my r squared, so that'll be 1 minus that r squared. X squared plus y squared is r squared. Then what we have to do is change that to our limits of integration. So we have to note that x squared plus y squared is a circle of radius 1. That would mean that my r would go from 0 to 1, as noted here, and my theta, because this is in my first quadrant, would go from 0 to pi over 2. So just extending everything, and we're going to do some problems with this. This is a general explanation of how we go from our one set of xy plane variables or values to that UV plane. We will say that R is going to be the image of S under this particular set of equations T. So if I'm looking at some sort of R and theta set of variables, and here are my boundaries, those boundaries in the xy plane would be the fact that r is a radius, so I have this radius of 1, and then it being in the first quadrant, so that's why it's going from 0 to pi over 2. Notice that this D is just a point in this xy coordinate system. And then they go through a nice table with some boundary equations and then showing you how these boundary values occurred. And to me, the pictures are exactly what I need to kind of figure this out. Now, in going from one plane to the other plane in a different set of variables, we need to note that it's not a one-to-one transformation from S to T or T to S. The boundaries do remain the same, but we just have to figure out what they equal in those different in that different coordinate system. This is going to involve something called a Jacobian determinant, and we will need to find the Jacobian determinant so that we can then go from our R plane to our S plane, so from our rectangular coordinates into this UV set of variables, and it will be our different functions and how they relate multiplied by the absolute value of that determinant, and then our du dv. So we're going to find the Jacobian in example 2 because that's what they're asking us to do here. So let's just look and see what a Jacobian would mean. I'm going to need each of these partials, the partial of x with respect to u, the partial of x with respect to v, and in this case our u and v are r and theta. So let me write some of this out. Alright, so I'm going to find the partial of x with respect to r. So partial of x with respect to r, that would just be cosine theta here. Partial of x with respect to theta, that's going to be minus r sine theta. Partial of y with respect to u, or in this case r, so that would be just sine theta. Partial of y with respect to theta, and in this case that's going to be r cosine theta. Entering this into our Jacobian determinant, and this is going to be in terms of r and theta, and we'll place those values in here. Partial of x with respect to u, that's cosine theta. X with respect to v, that's minus r sine theta. And partial of y with respect to r, that's going to be sine theta. partial of y with respect to theta then is r cosine theta. Computing this determinant, you're going to get r cosine squared theta, and then you're going to get minus a negative r sine squared theta. Oops. And then doing a little bit of algebra here, you'll note that we have an r in both cases. I'll pull it, and I have cosine squared theta plus sine squared theta, which we know to be 1. So this equals r, which is a very nice feature, because if you'll notice here, that means if I'm going from rectangular coordinates to polar coordinates, this would just be whatever my function is, and then r dr d theta, which was what we had before in with just our single integrals. In example 3, they give us the transformation that they want us to use. Here is our t. Here's my equation sitting right here. Note that my equation is going to look like this: double integral r square root of 2x happens to be for u, just replacing. And if I look at this y minus 2x, I'll see that that happens to be v. So I'm just going to say for uv is what this is going to look like inside this integral. Alright, so let's get moving on our Jacobian, because we're going to need that. Whoops, that wouldn't be under the rectangular coordinate system if I wrote it like that. That's going to be s. And then I'm going to need my Jacobian, and then I'm going to need du dv. In order to get this Jacobian, I'm going to need the partial of x with respect to u. This is going to be a 2 here, partial of x with respect to v, 0, partial of y with respect to u. That's going to be 4. Partial of y with respect to v, that's going to be 1. This gives me my Jacobian is equal to, I need partial of x with respect to u first, 2, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. And if I do this determinant, I'm going to get that this is 2. So my integral that I'm supposed to evaluate now looks like this, and we can use our transformation equations to get these values in u and v, these boundary point values that I need in order to get my limits of integration. So I would just plug them into these equations to get them. For my u, that's going to go from 0 to 1. For my v, that also goes from 0 to 1, and now it's just a matter of solving this integral. And here is this integral in completion. A fairly straightforward integral. Alright, on to the next one. In our next example, they just give us this picture here. They say we're going to integrate it with using this function, and here are vertices. So if I look at drawing this out, I see that each of these boundaries follows y equal x or y equals negative x. If I were to rewrite this and say that each one of these is some constant x minus y, or we could say that it was, and just move this to the other side there, some constant x plus y, then what I can do is say, let's let this one be u, and we'll let this one be v. And I could have swapped it to either side and made either one of them, I could have made this y minus x, so it'll still be the same thing in the long run. But this would be my u and v equations. Now I need to rework each one of these so that it's in terms of x equals with just a u and a v. So I'll do that for each one. And here's the algebra of going from the u in terms of x and y to x in terms of u and v and y in terms of u and v. I'm going to need this for the Jacobian, so I just went ahead and found that, and that's how they got this set of transformations here. And once you get this set of transformations, just go to your boundary points and then you can get these values here that they have for my u and v on those boundary points, because those are going to be my limits of integration. So let's set up this. First I'm going to find the Jacobian, and then I'll set up this integral. Alright, moving stuff around, I'm going to take my partials so that I can get my Jacobian. Partial of x with respect to u, in this case will just be 1/2. Partial of x with respect to v, that's a half. Partial of y with respect to u, minus 1/2. Partial of y with respect to v here is positive 1/2, and then finding my Jacobian. Here we have our Jacobian set up. To get our limits of integration, they've already computed those in this square here. We would see that u goes from 0 to 2, and v also goes from 0 to 2. So we're just going to perform this integration, which will be fairly straightforward. Just breaking this square root apart, putting each of these to the 1/2 or to the negative 1/2 power, and pulling constants out front. It'll be fairly straightforward. Okay, just moving on with this integral, and just integrating with respect to u. I'm going to replace these limits, then I'll integrate with respect to v and just get my answer. Alright, and here's finishing up this integral. You could compute the approximate value if you want to punch this on your calculator. Alright, first up they've given me some sort of region that's bounded by these parabolas. If I look at this pair and this pair, I can determine my u and v equations. If you'll notice, this is some sort of constant with x minus y squared. So let's make this be u equals x minus y squared. This one is going to be some constant that I can write as x plus y squared. So we'll let this one be v equals x plus y squared, and that's how these u and v equations were developed. To get the x and y in terms of u and v, you'll just plug each of these into the other until you get to that point. These are necessary so that I can get my Jacobian, and I'll need the partial of x with respect to u and so forth. So let me write that down. Alright, there's my partials computing my Jacobian. I get this. So my integral, which is this in the rectangular world, now becomes, now it is y squared, so here's my y, and I'll just square that, and you'll notice the square root drops, which is very handy. V minus u over 2, and then my Jacobian, this one isn't quite so pretty, let's see what we get here, 2 square root 2 v minus u, and then it's du dv. Limits of integration were already computed here. Limits of integration, just compute your boundary points using these equations. And for u, it's going to go from the 0 and negative 4, and then 9 and 16. So I'm going to do a little algebra here. Wow, this one gets really simple. If you will just make sure and rationalize that denominator, you'll end up with this. And at this point, I can now integrate with respect to first u, then v, and I will come out with my answer. Alright, what a mess that is. You can punch this if you want to on your calculator and see what the approximate value is, but here's your exact value of that integral, and it is not necessarily what I would call pretty. Alright, on to the next one. What we're going to do here is extend what we have been doing to 3 dimensions, so we are going to do this in 3 space with a triple integral. Note that my Jacobian is just extended to 3 variables, taking the partial for each one with u, v, and w on your x, y, and z. And your function still would remain the same, but with that change of variables multiplied by, of course, the absolute value of the Jacobian, and on that du, dv, dw. transformation. Imagine we're getting ready to do a problem with that. Alright, here are our boundary planes. Let's look at this pair, then this pair, then this pair. If I was going to rewrite this one, I might say that it is some y minus x equals c. So let's let this be u equals y minus x. This one, we're going to say that this is some z minus x equals c. So let's have that be v equals my z minus x. This one is just a z, so let's just say w equals z. And this will be my transformation equations. I need to rewrite this so that it is x, y, and z in terms of u, v, and w only. So let me do that algebra. Alright, so for my z equation, I get this. For my x equation, I get z is w, so just w minus v. There's my x. For my y, y is equal to u plus x. I know the x is w minus v, so that's going to be my my y equation. And now I'll need my Jacobian, so I'm going to have to get all of those partials. Alright, we've gotten the Jacobian for this, so let's see, my integral is going to look like x is w minus v, and z is just w, and this is going to be du dv dw, getting my boundary points and figuring out that u is going to vary between 0 and 2, v between 0 and 3, and z varies between 0 and 4. Now this is a fairly simple integral to evaluate. I love it when they fall out this nicely. And there we have it. And let's see what we have next. I've included in your notes strategies for choosing new variables. Hopefully you've gone through how it is that we decide what to pick for u and v, and if you have any question about that, be sure and email me or see me at the Collaborate. Thank you for listening.